Okay, sorry about that. So I realized halfway through this problem that I had factored wrong, duh. So I fixed it and we're starting over. Here we go. So what we're gonna do is we're gonna pick numbers, or sorry, we're gonna draw a number line, and it doesn't have to be evenly spaced or anything fancy, but you're gonna put your critical numbers on the number line, and you're going to determine what's going on to the left and to the right of each of those critical numbers. All you have to do is you have to pick a value that is in the window that you're looking at, meaning in this case, anything less than -1. So I'm going to pick -2, and I'm going to plug it into my derivative, which is any one of these things here. When I plug it in my derivative, I want to know whether the derivative value that I get is positive or negative. If it's positive, that means your function is increasing. If it's negative, that means your function is decreasing, okay? So this is going to tell us about the trend and the shape of the graph. So I'm going to plug in -2. I'm going to plug it into this factored form. That's what I like to do. You can plug -2 in all the way up here if you want to, but the main goal, by the way, is just to get whether it's a positive or a negative answer, okay? So if I plug in -2 to this factored form, I know that this group, when I multiply by 12, that's negative something. -2 plugged in here is negative something, and -2 plugged in here is negative something. So that's going to give me a negative answer, which means that my graph is decreasing from -infinity to the first critical number, which is -1. Okay, let's repeat that process. So I'm going to pick a number that's between -1 and 0. Those are my next critical numbers. Pick a number there. I chose -1/2, and do the same thing. Plug it into your derivative. So -1/2 plugged in here is -6. Plug in here, it's negative something. Plug in here, it's positive. So we have a negative times a positive, which is a positive answer. I don't know exactly what the answer is, but that doesn't matter. It's just a positive number. And so I know that section of the graph will be increasing. And then I'm going to continue doing this. So I'm going to plug in 1 for the next thing. That's a positive times a negative times a positive. That's negative. So that region will be decreasing. And then the third, I'm going to pick x equals, or the fourth interval, I pick x equals 3. 3 plugged in would be positive, positive, positive. So that's a positive answer. And that means the function's increasing. By the way, one more time, if you don't want to plug it into this factored form like what I'm doing, you can just take the number that you're testing and plug it into the original derivative and then go from there, okay? All right, so here's what this means. Find where the function is increasing and where it is decreasing. Our function is increasing from -1 to 0 and from 2 to infinity. Our function is decreasing from -infinity to -1, and then again from 0 to 2. Okay, so that's not too bad, I don't think. Okay, now how does that relate to maxes and mins? Well, when a function's increasing and then it switches to decreasing, that actually tells you what's going on in between. So if we go back a second, our function here at the beginning was decreasing, and then it switches to increasing. That means the graph was like this one at the top right. It was going down, and then it switches and starts going up. What's going on here in the middle? That's a minimum, right? If you're going down and then up, you have a minimum in between, okay? If your function goes from increasing to decreasing, what's happening in between is you have a maximum. You follow me? Now, it's possible you could have a function that's increasing and then increasing more, which means you would have no max or min. It would look like this one down here on the left. Same thing on the right. If you have a function that's decreasing and then decreasing more, there's no max or min there. That has a special name that we haven't gotten to yet, but that is not a change in direction. So there's no max or min. You're looking for a change in direction. Okay, so that means back here, this wasn't required for this question, but I'm going to add it on just so because we just talked about it. So if my graph is going from decreasing down to up, that means that -1 is a local min. If we're going from up to down, that means 0 is a local max. And decreasing to increasing means down to up. That means that you have a minimum, a local minimum here. Okay, we're going to look at that a little bit more. So basically all that stuff I just told you has a name called the first derivative test. And it just simply means that if you have a function that changes direction from increasing to decreasing or vice versa, that you're going to have a min or a max in those locations. So this is a little cheat sheet for you, okay? Refer back to this whenever needed. Let's try that again. So we're going to find all the local maximums and minimums. So we kind of already did that using, this was the exact same equation as number 1, right? And so I already told you that if you go from down to up, there's a min, or from up to down, there's a max. So let's pull this information over. The minimum is at -1 and 2. Go. So you have a local min at x equals -1 and x equals 2. And this is all from example 1, one we just did. You have a local max that occurs at x is equal to 0. Okay? Here is a question involving trigonometry, same exact concept. For the sake of time, I'm going to skip over this one and ask you to look over this later. So maybe grab your phone and take a picture of this one real quick. I set it up a little bit differently, more of like a chart style rather than a line. It's all the same, so you can choose which way you like better. But maybe take a picture real quick and come back to that one later. But let's keep moving, okay? So we're going to do just a quick observation or exploration thing here. So there's another little characteristic, basically something that could happen with your graph, okay? So let's say that this is a chart, and what this means is that there's a critical number at 1 and there's a critical number at 25, okay? And you have a graph that's going from decreasing to increasing to decreasing. That could look like this. Decreasing, increasing, decreasing. You see it? Okay. Could also look like this. This graph looks odd, but this graph does have a decreasing area, an increasing area, and then decreasing. Same thing with the critical numbers. Those are not wrong. So how do we know whether our graph looks like the top one or looks like the bottom one? It's very hard to tell because based on what we currently know, it fits the same description. Okay, obviously they have strikingly different features, but we don't know how to describe them yet, but we're about to learn right now. So here is your new vocabulary word, concavity. So concavity is a way to describe the shape or the curvature of your graph. So if I told a 5-year-old to draw a bowl, this is what it would look like in red here. We would call that shape or that type of curve concave up. So if it looks like a U or a bowl, it's called concave up. If it looks like an upside down bowl or an upside down U, that's called concave down. And knowing that word concavity would be very helpful here in this situation, okay? So here's your elementary description of concavity based on a 5-year-old's perspective. Here's your calculus nerdy version. So in concave up curves, the tangent line, it will be drawn underneath the graph. Okay, so if I drew a tangent line anywhere on this curve, it would be underneath the line. In concave down graphs, that's the opposite. So if I were to draw a tangent line anywhere on this blue curve, it would be above the graph. That's like the nerdy version of concavity. So concavity would have helped a ton here to determine what's going on. So if you look right here from on this first graph from negative infinity to, I don't know, somewhere between 1 and 25, that looks like a bowl shape. So that looks like concave up, where this graph is definitely concave down. So the concavity, had we known that, would have helped us choose what our graph would look like. Okay. The piece of information that's missing until this point is that a function will be concave up like a bowl if the second derivative is positive. And it'll be concave down like an upside down bowl if the second derivative is negative. All right, so let me show you what happens to a curve when the second derivative is 0. So, you know, when the first derivative is 0, it's like a max or a min, probably. What about when the second derivative is 0? So let me draw a curve. Nothing real crazy here. Not like that. Let's try this again. Okay, that's going to have to work. So a point of inflection is a point where the function flips concavity types. So when you have a graph that goes from a bowl shape to an upside down bowl shape, that's called a point of inflection. So look at this one I just drew. We have a bowl shape here, that's concave up, and we have a concave down in this region. So wherever they start to flip and switch directions, switch concavity, that is called the point of inflection. Okay, there's actually another point of inflection on this curve that I drew, because right here we switch from concave down to concave up. So I would say this is also approximately a point of inflection. We got 2 of them there. Again, key characteristic of that switch is that the second derivative at that location would be equal to 0. Okay, so example 4, this is where it gets a little bit tough because you're now going to sketch a graph, okay? All I'm going to give you is a whole bunch of information about increasing, decreasing, concavity, and then even limits, which tell you like end behavior. So there's not really an easy way to do something like this. It's a puzzle that you have to kind of figure out. So maybe let's decode what all these things mean. Like in the first set of criteria, it says when f prime of x is greater than 0. That means that the slope is positive, which means that the function is increasing. Actually, let me just write increasing. So we want to draw a curve that's increasing from negative infinity to 1. And then here the slope is negative. So that means it's going to be decreasing from 1 to infinity. So it's going to be going up and then down. Okay? And that happens at 1. That happens at 1. So we'll make 1 right here. It's going to go up and then down. That's all we know so far. Okay. Part 2 tells us the second derivative, which means concavity. The second derivative is positive. So that means it is going to be concave up from negative infinity to negative 2. So I need negative 2. There's negative 2. And then from 2 to infinity. So we'll make this 2 over here. Okay, so that's concave up like a bowl shape. And then the second derivative is negative, which means it would be concave down from negative 2 to 2. So that's tricky. I need it to be upside down U, but I need it to still be increasing. Okay, we can work with that. And then the limits, as x approaches negative infinity, that means that the limit is going to be equal to negative 2. So that's like the y value. It just tells you like the height, I guess. So as x approaches negative infinity. So that means the graph, if I go to the left, is going to sort of like level out. There would be an asymptote here. Okay, so that's helpful. And then the same thing up here, the limit is going to be 0. So on the right side, it's going to level out at 0. I don't know if it's going to be coming from the bottom or the top, but we can do that here in a moment. Actually, it'll be coming from the top because it's decreasing. So it's going to level out at x equals 0 there. Okay, so we've got a beginning and we've got an end. Let's just kind of start and we can kind of adjust and redraw as needed. So this beginning portion, I need to be concave up like a bowl, and I need to be increasing. So we are concave up until we get to -2, and then it flips to concave down. So I need to be increasing until I get to -2, and then I'm going to flip and go like the other direction. So here's a bowl, very mild, not real sharp curves here, but and switch, I'm going concave down until I get to 1. So concave, I still got to be increasing though. Going to be increasing until I get to 1. That's pretty good. So then at 1, I've got a maximum because I'm going to switch and go downward. So I'm going to go down. Geez, this is like a max here. But I'm going to go down, still concave down until we get to 2, and then it says go to concave up. I really wish this wasn't such a terrible looking graph. I'm so sorry. Let me try that again. So I need to go round it down and then switch to rounding up. I just really can't draw on this airliner, you guys. I'm sorry. But that's supposed to be rounded. There we go. That's a little better. Rounded a bit. And then at the very end of the graph is supposed to level out at x equals 0. It's definitely not leveling out. We just have some mercy here and say good enough. There we go. Okay, that obviously I'm having trouble with that because it's not an easy task. So if you don't get it right away, please be patient. It will come. It just takes some practice. All right, we've got one more example, okay? One more thing to show you and then one more example. So discuss the curve with respect to concavity, inflection points, and relative extrema, and make a rough sketch. So we're going to start by doing the first derivative. And we're going to find all of our critical numbers. So factoring and solving is required here. Okay, critical numbers for the first derivative are 0 and 3. I will come back to that in a moment. Let's do the second derivative. The second derivative would be 12x squared minus 24x. We're going to do critical numbers for that as well. So we're going to factor out a 12x. And we're going to solve and get x equals 0 and 2. Okay? So remember, the first derivative tells you increasing, decreasing. And the second derivative tells you concavity. You have to compute them separately, okay? We are going to continue what we did in the previous examples, where we would draw a line or a chart, and we would break it up with the critical numbers. I'm going to put 0, and I'm going to put 3, and I'm going to find whether the derivative is positive or negative, whatever, in each of these regions. So I'm going to pick a number that is less than 0, pick a number that's between 0 and 3, and pick a number that is larger than 3. When you do your testing, all of these numbers get plugged into your derivative, and you tell whether it is a positive or a negative answer. We have, I'll just go ahead and give you my results. I had negative, negative, positive, which means our graph is decreasing, decreasing more, and increasing. Okay? let's go over and repeat that exact same process for concavity. So we're going to use 0 and 2, because those are our critical numbers for concavity. We're going to still pick numbers that are in those intervals. And we're still going to test them, but we're going to plug them into the second derivative because we're dealing with concavity and those two things go together. So if I plug in -1, I'm going to get a positive number. Then I'm going to get a negative, and then I'm going to get a positive. So that means my graph would be concave up, concave down, concave up. Okay? Now let's add a little bit more information to this little chart. Remember that if you have a graph that switches from increasing to decreasing or vice versa, that means you have a max or a min there. So on this first chart with the first derivative stuff, we go from decreasing to increasing. We go from down to up. So that means that 3 is a local min. Okay? 0 is not going to be a min or a max because it goes from decreasing to decreasing. So you're going down and then down more. So nothing is happening there as far as maxes and mins. Over here, if you switch concavity from concave up to down or vice versa, that means the number in between is a point of inflection. And that happens twice here. Okay, that's where your graph switches concavity. So we have 2 points of inflection and 1 local minimum. And I think it helps a little bit with the graph sketching if you know that information. So we're going to get a graph drawn here. I'm going to be starting pretty darn close to 0 because I have a 0 critical number. 1, 2, 3. Got critical numbers throughout that as well. That should be good enough. Okay, so how are we going to draw this? I don't know. I think maybe I'm going to go to the minimum and maybe pick where I want that to be. So the minimum's at 3. I'll just put a dot wherever, and I'm going to, in my head, say that's a minimum. So it has to be already off to a good start. If this is my minimum value, that has to be like a bowl shape, like concave up there. And if you look at that interval, it does say concave up. Then maybe I'll put a couple points of inflection. So I need a point of inflection at 2. So right here, I need a point of inflection. And then I need another point of inflection at 0. Okay. So I'm going to kind of go backwards, I think. From 3 to infinity, the graph is supposed to be increasing. So that part's pretty easy. From 3 to 0, we're supposed to be decreasing. Oops. Okay, so if the graph is decreasing from 0 to 3, so that means I need this to be a little taller. I need it to be kind of going down until I get to the min, but I want it to switch concavity along the way because it switches concavity at 2. So we start with concave down and we go to, so we start with concave down like this, and then we go to concave up when we get to 2. So I'm going to kind of make this an easy transition. I hope something like that would work. From negative infinity to 0, we go back to concave up. So I need to switch concavity right here. That's going to be a little bit tricky. My graph is still decreasing, so I'm going to need a little more room. And I want to switch to concave up. So it's got to go kind of like at 1, we got to switch and go the other way. So that might be good enough. It's not great, but it works. So we kind of go bowl shaped up here, switch to concave down, and then back to concave up. Again, rough sketch. It's going to be the name of the game. All right, that's it. This homework might be a little tricky for you. Give it a try, see how you do. Example 6 is also one I would like you to try. So again, you can take a picture of that and see if you can work through it. I'm going to circle the answer for you. I believe it is C. See if you end up finding the same answer.